Hi there, Dr. Steve Kuchnicki again, and what I'm going to talk about today is this is the first of a couple that I'm going to have to do on this topic, I would think. And this is the why of failure theories, failure theory background. I mean, why do we have different theories of failure? And the basic fundamental, I would say, comes down to this situation here, let's say, right? If I draw a little stress block, and I put my coordinates on it, and if I give it some axial stresses in the x and y direction, right? And I give it a shear stress. And I'll draw the shear stress to be positive. Let me get rid of that guy, right? I'll draw in my shear stress, like such, right? We cannot do the thing that seems like we should do, right? We cannot predict failure simply by comparing sigma x and sigma y to yield strength. That's the naive thing you'd like to do. You'd like to be able to look and say, okay, well, let's just compare the x-axial stress or the y-axial stress to the yield strength. You can't do that. It doesn't work that way. Because what experiments show is that if you try doing that, bad things happen. You start predicting safety where you have failure, bad things. Or, the other thing we can't do, we also can't compare the shear stress to the shear yield strength. We can't do that. Because what happens is if we do that, we start to predict safety where failure actually happens, right? And that's just not a good thing for us. We want to be able to predict things that, reflect reality. So what do? What we have to do is we break this down into two parts, okay, into two separate sort of branches. And there's a reason for that too, okay? So what we do is we break this, and this is going to be the high level thing here. I'm not getting into much detail about any of these theories in this video. There's going to be others that handle that part, I should say. We break it into theories based on whether the material is ductile, and hopefully this is a word that you've heard before if you're looking at this, because it means it stretches a lot before it breaks, right? Or the opposite of ductile in this sense is brittle, something that doesn't stretch much before it breaks. Ductile, you want something that's really ductile. Take rubber, for example, right? But steel is pretty darn ductile. Aluminum is really ductile, especially if you heat treat it the right way, right? You can make it very weak and ductile. Fine. Brittle, first thing I think of is usually glass, right? Or cast iron is another great example of that, right? These are materials that don't stretch a lot before they break. Concrete, another great example of that, okay? And the reason we have to break down into ductile or brittle is that it turns out the way these materials fail is different, okay? So let's say you did a uniaxial tension test, all right? And usually, these are done on cylinder-shaped specimens. You can do them on other shapes too. I've had students do that way. I've done them myself on other shapes. Dog bones, typically, because you want to make sure that you have the location where failure is going to occur pretty well handled, right? Pretty well picked out. So you do tension tests on a cylinder-shaped specimen, and you get two different results. Aside from the fact that the ductile material stretches a lot before it breaks, and by a lot here, we're talking 4 or 5% strain at elongation. Usually 5% is the number I see people use. Sometimes I see people use other numbers, but it's usually 5%, right? And when it breaks in kind of a funny way, because the specimen always starts off looking right? Like I'll draw it in purple just so it's a little different. It looks, the ones I used look a little bit like this, and this is a standard from the American Society of Testing Materials. I think they've changed their name to ASTM specifically. They changed their name to their acronym, whatever, right? But these ends here are threaded, right? And this center part is a standard 0.505 inches. Why 0.505? It's close to 50 millimeters. You know, that's pretty much the idea. Right, the metric inch is essentially 25.4 millimeters. That's kind of the way it goes. Right, actually it's not 25.4. It's not. It's more like 12.5 millimeters. I went the wrong way. I apologize. Not 50 millimeters. 12.5. I multiplied instead of divided. I apologize. This thing is going to be about 0.505 inches in diameter. Okay, great. So again, that's about 12.5 millimeters. Okay. So if a ductile material is put in this and it breaks, and I'll leave out the threaded part because it's just more stuff to draw and really it's not going to add anything, right? What we get for a failure, we'll get one side that looks a bit like this, kind of like a cone, and we get another side that looks like this, kind of like a cup that's ready to accept the cone. So on the top, I've drawn the cone. On the bottom, I've drawn the cup, and it could be the other way around. It doesn't matter. It's not like this is set in stone that it's going to break with the cone on top and the cup on the bottom. We don't know that going in. It could be one way or the other. And what's funny about this cup and the cone is if you measure that angle, that's 45 degrees. Okay, interesting. And remember, of course, we applied our force like this. Our big specimen here gets a force that looks like this. Well, if I walk over to a brittle material instead, what I'm going to find is that my failure surface looks a lot more like this, where really this is like 0 degrees. It's perpendicular to the loading direction, if you want to think of it that way, right? So that might be the even better way to do it, is say this angle is 90 degrees, right? I'll even make that 90 degrees so we really highlight it. It's 90 degrees from the load direction as opposed to 45 degrees from the load direction on the left-hand side, on the ductile one. And of course, the ductile one also undergoes something called necking. It gets really narrow at the center. It's not 0.505 inches in there anymore. The brittle material gets really close to 0.505 inches. Well, what does that mean? Okay, that's what this means is exactly the reason why we need to know about different failure theories for different materials. And the way to think about what this means is to draw a stress block right in the middle of that specimen. And if I look at that stress block, right, if I take and I highlight that stress block down here, what I'm going to find is that if I then put my X and Y coordinates in here, well, I think you'll agree. If I'm just applying that single force, that force gets to do one thing. That force is pretty much through the center of the specimen. Looks like force over area, right? So what I'm going to see here is some stress sigma y. That's it. Nothing else. So I've got some normal stress sigma y on that orientation. Well, sure enough, if I look at the failure surface here, well, for the brittle material, right? The brittle material well, since it failed perpendicular to that principal stress, that's my largest principal stress, by the way, because my other two look like they're 0, right? So I've got no stress in the X direction. I've got no stress coming out of the page at me. So my biggest principal stress is sigma y. There's no shear stress, right? So it must be principal. The brittle material, it fails due to the normal stress. Okay, which makes some sense. We applied a normal stress, failed because of the normal stress. Great, no problem. Ductile material takes a little more thought, though, right? Because the ductile material, well, my failure plane is really sitting on these axes that I'll call, let's call them y prime and x prime, right? What stresses do I have there? Well, what's going to happen with the ductile material, I should say, is if I take and draw myself a little quick Mohr's circle, yes, a little Mohr's circle, right? Tau and sigma. Well, I know I've got sigma y out here. There's sigma x. So my circle, and excuse me, it's probably going to stink because I'm freehanding it on a screen. I'm going to take that circle and walk. That's not half bad. Okay? I know I want to go 45 degrees. So I have to go 2 times 45 degrees to get to the x prime, y prime system on my circle. I've got to go 90 degrees. That's my angle to get from xy to x prime, y prime. So let's see, if I take and rotate to the left, here's going to be x prime, here's going to be y prime. Well, gosh, that's the maximum shear stress now, isn't it? Because I'm 45 degrees from principal stresses. So I've got the maximum shear stress there, right? The ductile material because its failure plane is at 45 degrees to where I had my principal stress directions, right? The ductile material fails due to shear stress. And just with that little bit of knowledge, that tells us right off the top that there is no way we can come up with one theory that covers ductile and brittle materials. We can't do it because they have different reasons for failure. There's different things going on inside that make material fail. The ductile material has a lot of permanent deformation. That's where all that ductility, all that stretch comes from. That's what all that stretch means, right? That means we're shearing atoms against atoms and moving things around inside the material. Wow, a lot going on, right? On the other hand, the brittle material doesn't have much of that at all. Again, I think of throwing a baseball at a glass window, right? It just doesn't go boom like some kind of a cartoon. It just breaks, right? So that means it's not stretching much, which means all it does is it just breaks and there's not much shearing going on. It's just getting pulled apart, right? That's what the normal stress does. So a brittle material fails because of normal stress. A ductile material fails because of shear stress. Something else going on inside of a brittle material, just to get into this for a second, is there's little cracks inside there. There's little cracks inside the ductile material too. But the little cracks inside the brittle material get worse because it turns out that the brittle material has those little cracks. They tend to grow faster because they have sharper tips in the brittle material. All kinds of bad stuff happens, right? So in the end, what we're looking at is we have two different mechanisms by which these materials fail. So that means we need to have two different sets of theories to describe why these fail. Okay, that statement right there is essentially the point of this entire video here, is to say, look, here's why we need it. Okay, up next, now I'm going to have some more videos that deal with the ductile failure theories and the brittle failure theories and where they actually come from.